In this video, we are going to be discussing modern atomic theory, which gives rise to the current knowledge that we have of how an atom looks like. In order for us to study modern atomic theory, I'm just going to place it here. We need to talk about what we learned previously. Early atomic theory established that atoms in an element are formed by three subatomic particles. In the nucleus, we can find protons and neutrons. Around the nucleus, we can have find the electrons. Now, understand that these electrons, by the end of early atomic theory, we don't know that if they have an exact location, if they are just placed randomly inside the atom, where are their locations, do they have energy, do they don't have energy. By the end of atomic theory, we just know that there are some negative charges that are circling the nucleus, and that's it, nothing else. Or actually, we don't even know if they're circling the nucleus. We just know that they are surrounding the nucleus because it makes sense, since the nucleus is positive, that they are going to be around the nucleus. Now, understand that it is important that we talk about modern atomic theory, because since in chemistry, the arrangement of the electrons is what determines the physical and chemical properties of these elements, it is important to talk about them. Now, there's going to be two theories that we are going to talk about in modern atomic theory. First is going to be the Bohr's model. And as you can see in the Bohr's model, we're going to have some rings around the nucleus of the cell, around the nucleus of an atom. And they are going to represent the electrons. So these gray dots that we have here are the electrons. Okay. Now we are also going to be talking about Schrödinger, because Schrödinger developed a series of equations that gives us the location where an electron can be found in an atom to a 90% accuracy. So this is actually the current model that we still use, even though it was discovered in the 40s. And we're going to talk about them in detail in this section. Now, in order for us to understand all these processes and all these discoveries, we need to understand how electrons are at their core, meaning what are these particles made out of? So, understand that electrons have what are called atomic spectrums, okay? An atomic spectrum describes the frequencies of electromagnetic radiation, in other words, light waves, during transitions of electrons between energy levels. So understand that each one of these electrons that are part of an atom are going to be transitioning, and that is going to give rise to the production of light specifically. And since electrons are moving particles, they have energy. However, they have a specific allowed energies that are known as energy levels. And that's where we're going to center our discussion when we talk about the Bohr model, because Niels Bohr was the first person that actually put this in the context of electrons. So understand that in general, in the Bohr model, which we're going to talk about more in detail in the next slide, he represented this energy where the electrons live as rings, as we can see in the first image. So we have the energy as n equals 1, n equals 2, n equals 3. So the energy levels are going to increase as we move outside of the nucleus. Also understand that as we move outside, there's an increase in energy between the different rings, okay? To utilize an analogy, so you guys remember that energy is increasing as we move outside, this is kind of like if you have a bookshelf and you're trying to reach books, it will be easier to reach a book that is in the bottom because it will be less energy than the one that is on the top. So just imagine that the bottom of the bookshelf, that would be an area that is closer to the nucleus, if we want to think about an analogy. But at the end of the day, understand that this atomic spectrum is going to give rise to light. And this light is going to be a specific color in the visible spectrum. So here, to represent the visible spectrum, I just wanted to point out that if you take sunlight and you pass it to a prism, then you're going to have the visible light spectra continuum, because that's how we process sunlight. But understand that when we look at this experiment, these electrons are not going to give a continuum, it's going to look different. So let's now explore what is first the electromagnetic radiation, and then we're going to proceed to talk about the Bohr model in detail. So I just wanted to point out that in the larger view, the sunlight is part of what we know as the visible light spectrum, which is one of the components of the electromagnetic radiation spectrum, okay, which shows the arrangement of wavelengths in terms of the different types of radiations that we have out there. Now, in this image, I am not expecting you guys to memorize any of the context of it. Just understand that many things that are part of the electromagnetic radiation spectrum are involved in things that we utilize in everyday life, including the microwave that you may utilize to heat up your food, the cell phone communication, how we get a television signal, how do we get an AM or FM radio signal. All of this is part of the electromagnetic radiation. But now we're going to focus on the visible light spectrum, because that's the one that is related to the atomic spectrum, okay, that it is illustrated by the elements or any other atom. So let's now talk more in detail about the Bohr model. Okay, so Niels Bohr developed a model of the atom, as you can see, around 1910, to explain how the structure of the atom changes when it undergoes energy transitions. So Bohr's major idea was that the energy of the atom was quantized, and that was very important because up until this point, we didn't know that electrons lived in quantized energy levels. Bohr proposed that the electrons were surrounding the nucleus like planets surround the sun. That's why these rings, he said that the electrons were in orbits. So that's what he called them. Now, when he was developing his mathematical equations to understand the discoveries that he was doing with specifically hydrogen, understand that it came all from the following experiment, which is illustrated in the second image. I'm just going to zoom in. This is the experiment that Bohr was doing. He had a tube that contained hydrogen gas, and as you can see on the image that I have here to its left, that's how it actually looks like. And then he was taking that light that was coming off out of the tube, and he was passing it through a lens, then passing it to a prism, and then he was capturing it in a photographic plate. In that photographic plate, as you can see, he saw very distinct lines that showed that this is the atomic spectrum for hydrogen. Okay? Then he developed a set of equations to understand how are the movement of the electrons within this ring system, these quantized energy levels, explain these colors that were captured. Okay? So the idea that he put forward is that the electrons, and let's just say that the electron lives right here, okay, was going to absorb energy, and it was undergoing excitation. And excitation means that it's going to move from a lower energy level to a higher energy level after it absorbed some energy. Then, after the electron got excited and it was in this new energy level, understand that he proposed that this electron, okay, I'm just going to do dotted line because you have to imagine that this electron is moving, undergoes the process of relaxation. And in relaxation, that we're going from a high energy level to a low energy level. Okay, and when this happens, then light is emitted. And this light emission that we see here, I'm just going to highlight it so we see the connection. This light emission is what gave rise to these lines. Okay, that's what he was proposing. So all of the work that he did was great and it worked awesome. Remember that he was working with hydrogen. So in this process, he only had one electron to worry about because that's what we have in hydrogen, only one electron. So everything worked very nice and no problem. So he decided to just apply his model to other atoms. Let's say 2 electrons, 3 electrons, so on and so forth. Now, let me illustrate to you guys how the light spectra actually looks like for other elements. And here we have helium. And helium specifically has 2 electrons in the system. Lithium has 3 electrons in the system. Oxygen has 6 electrons. Oh, sorry, it has 8 electrons. Carbon has 6 electrons. Nitrogen has 5 electrons. Neon has 10 electrons. Okay, so I just wanted to illustrate that as we increase, how complex does this become? So this is exactly why Bohr got into trouble, because even if we compare 2 electrons, 3 electrons in a system, understand that all of a sudden, if I zoom in, there's other lines that appear in the spectrum. And the model that he designed for hydrogen didn't work for things that had more than 1 electron. Okay, just because of the complexity of how do we now explain all of these lines in terms of transitions. His mathematical model wouldn't work for things other than hydrogen. So understand that from there, a new model needed to be proposed. And that's what brings us to the quantum mechanical model of the atom, which was developed by Erwin Schrödinger. Now, as you can see, Erwin Schrödinger applied the mathematics of probability and ideas of quantizing energy levels. Remember that quantizing energy level idea came from Bohr. Okay, he did that discovery. So Schrödinger applied that quantized energy level idea to physics equations that described waves. So he developed a set of equations that predicted the probability of finding an electron with a particular amount of energy at a particular location in the atom. And to date, we still use Schrödinger's equations to understand the position of these electrons in these atoms. Okay? So now let's talk about these probability equations. Okay? Instead of looking at the equations, which are very complex, let's just look at the probability maps that they described. And as you can see, they are illustrated in this slide. So the probability maps, which we know them now as orbitals, okay, represent an area where we can find an electron to 90% accuracy. Okay, so in this, I'm just going to separate them so it's a little bit easier. As you can see, we have a probability map here We have 3 probability maps here. We have 5 probability maps there, and we have 7 probability maps in the bottom, okay? He determined, okay, that these are going to have a particular name. And these are the names for these probability maps. We have the S, we have the P, we have the D, and we have the F. Okay, those are our probability maps. He also determined that each one of these probability maps can work for 2 electrons. So, because of the number of electrons that are on each model of these probability maps or orbitals, then we can actually calculate what is the maximum number of electrons that can be found on these orbitals. So for the S orbital, it will be 2 electrons, and we're going to place it as a superscript. For the P orbital, we can have a maximum of 6. For the D orbital, a maximum of 10. For the F orbital, a maximum of 14. Okay? And that's just because the number of probability maps, and because each probability map will hold 2 electrons. Okay? Now, remember, in this model, we also have quantized energy levels along with these probability maps. Okay? So the probability maps that I just illustrated, those are what are called subshells. So these are the probability maps. Now, remember that these probability maps are going to be in a quantized energy level. In that quantized energy level, we know it as a shell. Now, only for the first 4 shells, there is a trend. Okay? The value of the shell is going to correspond to the number of subshells. Okay? And then on the 3rd column in this picture, we see which subshell actually lives there. Okay? So, for the first shell, we only have 1 subshell, and it's only S. For the second subshell, for the second shell, we have 2 subshells, and they're S and P. For the 3rd shell, we have 3 subshells, and then the subshells present are going to be S, P, and D. In shell number 4, we're going to have 4 subshells, and the specific subshells that are there are S, P, D, and F. We do not have any more subshells other than S, P, D, and F. So as we move on to, for example, shell number 5, shell number 6, shell number 7, which are the only ones that we know to date. 5, 6, and 7 are not going to have S, P, D, F specifically. Because, for example, shell number 5 also has 4 subshells. So this trend of shell number tells you how many subshells only applies to the first shell all the way to the 4th shell. 5, 6, and 7 have different number of subshells. Okay, so understand that the shell number is the energy level. Okay, and then the subshell is the orbital shape. Okay, and that's what I mentioned previously. Understand that in the textbook, they are mentioning about specifically the electrons that live in a particular shell, and they just tell you the total number of electrons in it, And that's because they are taking into account. So for example, if I illustrate this image in the bottom, first shell, it has one subshell, okay? And because that subshell is the S, and S can only hold 2 electrons, that's why you see the number 2 here. In the second shell, there's 2 subshells, S and P. The reason why we see 8 electrons there is because remember that the S orbital can hold a maximum of 2. The P orbital can hold a maximum of 6. That's where it comes from. And just to illustrate one last example, shell number 3, it has 3 subshells because the subshells are SPD, SP, and D, and S can hold a maximum of 2, P can hold a maximum of 6, D can hold a maximum of 10. If we add those 3, that's where the number 18 comes from.